Okay, so we are all here gathered for this very special colloquium. So let me first welcome Professor Jim Olsen from Princeton, who has kindly agreed to give this an overview talk on the Higgs discovery, and especially Higgs at 10 years. Before I sort of ask Professor Kajuri Mojumdar, my colleague here at TIFR, to formally introduce Jim, I would like to just give few words on the NSF Wednesday Colloquium, what it means to us, and also to the community that now is keenly following it over last 2 years through the YouTube channel. So the NSF Wednesday Colloquium has been an age-old tradition for TIFR itself. The Colloquium series is as old as the years TIFR has existed. The idea was conceived by our founding director, Professor Homi Bhabha, who basically thought it would be a fantastic idea if we gather the faculty and students in natural sciences, under one roof for one session of 1.5 hours of lecture and discussion, because it may propel within the institute discussions on active scientific topics of interest, as well as maybe bring collaborations to the fore. This has been a very successful series. Many students who had been participating in these colloquium series are now faculty themselves, and they actually recollect very nice training they received while listening to the talks here. So it's actually a pleasure to host this. For people before me have done a fantastic job of hosting this series. So today we have Professor Jim Olsen joining us from Princeton. A pretty early morning at in Princeton. So thank you, Jim, for doing this. And I have my colleague, Professor Kajuri Mojumdar, who is going to now formally introduce Jim and the colloquium talk. So Kajuri.
Thank you, Jyotishman. So good afternoon, everybody. A warm welcome to the special session of our symposium, celebrating a decade of the Higgs. Actually, since Monday morning, we are having really a grand feast about the magnificent science of the Higgs boson. Almost 100 years back, Indian scientist S.N. Bose got the idea and worked out the physics about the particles with integer spins. And Higgs boson falls into that category, but it's unique because this is the only observed particle so far to have spin 0. But that's not all. We have learned quite a lot during last 1 year since its discovery, but we still have to learn quite a lot. We have miles to go. But all these actually, you can say it's blink of time. We are talking about the science which happened almost at the beginning of the universe, 14 billion years back. And Higgs boson was postulated almost 6 decades back. And it is going to take the center stage of high energy physics for maybe next 2 to 3 years. Of course, we expect many more discoveries and LHCs with us for next 2 decades. So we are going to have really a very nice, exciting time. Without taking much more time, I would hand over the floor to Professor Jim Olsen. So it's actually a pleasure to introduce him. I know him, of course, for a long time. I don't remember whether, Jim, you remember me, because we went to Karlsruhe for the, I think, first Higgs symposium. That was maybe back in 2005 or 6. Mm-hmm. Do you remember that?
I do.
It was Carl Jacobs who organized it.
Yeah.
Okay. Anyway, so Professor Olsen obtained his PhD degree in 1992 from University of Wisconsin, working on CDF experiment at Tevatron PP bar collider in Fermilab, USA. Then he spent several years with University of Maryland. He was working on an experiment for bottom quark physics called Babar, that's in Stanford. Then he came to Princeton in 2002. And 2008, he joined CMS experiment, and he has been working mainly on Higgs physics. And his expertise has been mostly for Higgs to BB bar. The Higgs boson decays to bottom anti-bottom quark pair almost 60% of the time, but it's one of the most difficult, one can say, decay modes which we can detect and analyze experimentally. We have been hearing all those more, and today we will hear what we have learned till now and what is there in future for us. So Professor Olsen has been the Higgs physics convener. Then he became the overall physics convener for the CMS collaboration. And currently he is taking care of the responsibility of CMS experiment as the deputy spokesperson of the collaboration. So over to Jim. Thank you all.
Thank you. Can you hear me? Just check again.
Yeah, we can hear you.
Okay, good.
Yeah.
So thank you for that kind introduction and for the invitation, which I very much appreciate the opportunity to go back in time and revisit what was a very happy time for the LHC physicists and indeed for people around the world. So I hope to give you some flavor of that excitement and also talk about the impact of the discovery and maybe a few words about future, what you can expect to see from the LHC in the coming years. I understand the audience is broad, and so there may be times when some of you are bored, might be times when some of you are confused, but my goal is that not everyone is either bored or confused at the same time. And if that happens, it'll be somewhat successful. But let me proceed now, and I'm just to save bandwidth, I'm going to turn off my video, but then I'll turn it back on at the end if there are questions. So we're here to talk about some fundamental questions, one of which is, why did we need a Higgs boson? But really to answer that question, I think we need to step back further and ask two broader questions, two bigger questions, which the field of particle physics, of course, is targeting. What are the fundamental particles and how do they interact is really the goal of the research that we do, both theoretically and experimentally. And of course, these two questions are as old as antiquity, asked in different forms and answered somewhat successfully or unsuccessfully, as the case may be, throughout time. But by the 19th century, we had a way to organize the elementary particles at the time, which of course were the atoms, into an organized set based on the properties of these elements, and it was the periodic table. But of course, the periodic table did not look like that when it was first proposed. It looked something more like this. Not all the elements were known. There were some gaps in the periodic table, and there were even some elements in the wrong spot. But this idea of being able to organize nature in terms of the elementary particles, as well as we know at any given time, into a pattern that is defined by the properties of these particles is now at least 150 years old and quite successful. If you fast forward that 150 years, we have our own periodic table now. It's called the Standard Model of Particle Physics. And the particles in this model are organized as the elements in the periodic table according to their properties. And the basic idea is we have matter, which is fermionic, meaning each of the particles has half-integer spin angular momentum. And as Kajari mentioned, there are also bosons. These are particles of integer spin angular momentum. And in this model, the force carriers are all bosons. So to arrive at the forces that we know at the current state of the universe, we have electromagnetism, the strong force and the weak nuclear forces. And to get these forces, you simply apply in the Lagrangian, you construct a Lagrangian that has symmetries. And for each of the symmetries that you apply, if you ask for something called local gauge invariance, which I'll talk about, all of a sudden out pops the forces of nature in the form of these bosons, the so-called gauge bosons, which carry the forces. So the picture then we have in the standard model is that these fermions, the matter particles, they interact via the exchange of these force particles, the gauge bosons. For example, in Coulomb scattering, two electrons can repel by exchanging photons. But you can also have bound states, what we call hadrons in this case, the bound states of quarks, either quark-antiquark pairs called mesons or three quark pairs called baryons. And for example, you can get a proton with 2 up quarks and a down quark, and these strongly interacting bound states are what we call hadrons. So the Large Hadron Collider has the name because one of the particles that it collides are protons. So it's a very simple picture, and as the joke goes, it's so simple it fits on one page. This is the various Lagrangian components of the Standard Model, describing all of these particles, how they interact through all of the gauge forces. Of course, there are questions that remain. It's incomplete. The Standard Model as a construct is a quantum field theory that completely describes these particles and those interactions, but we know there's more. First of all, why is there a pattern? Why is this pattern? In chemistry, we have an answer to that question now, but we don't have an answer right now. Why these different families of particles with different masses and so forth? We don't know where all the antimatter went that was supposedly there at the beginning of the universe. We don't know why particles have the masses they do. We also do not know why they have any mass at all. That's one of the questions we're trying to answer today. And there are other questions that are related to different fields and different observations that have been made. And one observation we're trying to make, supersymmetry, but also what is the origin of dark matter? Are there more dimensions of space than just the 3 that we know about, and so on? So there are lots of questions. And of course, the Higgs boson most impacts this question of why do all the particles, these matter particles have any mass at all? Why aren't they massless? So to get more deeply into that question, we need to define what we mean by local gauge invariance, and to note that all successful quantum field theories obey this condition. And you can think of it as the gauge transformation as a phase transformation. So if you think of a sphere, you can rotate the sphere. And that in quantum mechanics, that would correspond to adjusting the wave function, the phase of the wave function by a constant amount, let's say theta. But you can also imagine twisting the sphere so that at each point on the sphere, you get a different rotation depending on its location. And in quantum mechanics, that would be the location in space-time. So X would be the position 4 vector. And so each point in space-time gets a different rotation, a different phase change. And this is what we call a local gauge transformation. And if you want your Lagrangian to be well behaved, you want it to be invariant to these kind of transformations where the phase can change at any point in space time. So as it turns out, so that's all fine, but for force particles that have non-zero mass, it breaks this local gauge invariance. You can't have that. And that's not good. And just one example, we don't have to get into the details, but if you write down the Dirac Lagrangian, which describes the interactions of electrons with photons in electromagnetism, you have a kinetic energy term for the free electron. You have an interaction term, which tells you how strong the interaction is between the electron and the photon. And then you have a kinetic energy term for the photon, which includes a piece that is proportional to its mass. So it's this term that is the problem, that if you have a gauge boson that has a mass, you can't make this Lagrangian locally gauge invariant. So for the electromagnetic force, it works because the photon is massless. For the strong force, it works because the gluon is massless. But for the weak interaction, and the classic example being beta decay, where a neutron can transform into a proton via the emission of a W boson, the charged carrier of the weak force, this W boson has a mass which is actually roughly 80 proton masses. So it has a mass, it's not massless. And so in the classic scheme of the Lagrangian, you can't make it locally gauge invariant. So we need a way, if we're going to include the weak interaction with the electromagnetic interaction into a big theory called the Standard Model, we need a way to get around this problem of the local gauge invariance. So the mechanism that was hit upon, we call it the Higgs mechanism, but there are many people who contributed to this. And there was an excellent talk in this symposium series by Rohini earlier on Monday. And I give the link to that talk if you want a longer history of the theory behind the Higgs mechanism.
Jim,
but just to illustrate,
there's a question, Jim.
Oh yeah, go ahead.
I'm completely outside the field. I'm a chemist, so I have very little clue of many of the things that you are sort of speaking. But one of the things that I would like to understand is the Lagrangian. Can you go back to the Lagrangian again?
Sure.
Yes. So, could you just help me figure out what the terms really mean here in terms of, I can see psi, gamma, and a differential of a psi, and then again the gauge interaction has multiple of those terms, and
Right.
so just a feel for it, then
Sure.
it will be helpful. Yeah.
So as in classical mechanics, where the Lagrange formalism was first used, one can extract the laws of mechanics by requiring certain conditions on the Lagrangian.
Right.
And they involve derivatives of the coordinates and also the time derivative of the coordinates, the Lagrange conditions. So broadly speaking, if you step back and don't look at the details, what this is the Lagrangian that describes a certain interaction of particles.
Right.
The particles have their wave function, and that
Okay.
is
Okay.
So the electron, you can think of psi here as the electron wave function.
Okay.
And we're applying, which is the analog of the position in classical mechanics in velocity. And so we're taking derivatives to get the Lagrange condition for this wave function.
Okay.
And if you inject electromagnetism, which has the electromagnetic force, in classical electromagnetism, you have the vector potential, which is this is the A here. So the vector potential.
The vector potential. Right. Okay. Okay.
And you can think of it very loosely. Theorists in my field might jump on me, but I think of the A mu as sort of the wave function for the photon. It's the vector potential in classical electromagnetism, but in quantum electrodynamics, it becomes a field of photons, and that's what this A is. So we're talking about electrons interact, and this gamma mu is essentially a kinematic factor which is what Dirac was adding to this. But he's trying to formulate in a classical Lagrangian sense the modern idea of a particle interacting with the quantum field. And so that's what this interaction term is. It's the electron interacting with the vector field of the electromagnetic field. And in classical electromagnetism, this would be the stress tensor for the electromagnetic field. Okay. And this is, it's not a self-interaction, but it's a kinematic term that is essentially the kinetic energy of the photon as it's propagating freely throughout space. So this was what you would have if you have a photon, a universe with just a photon in it. Okay. This is what you have with a universe with just an electron in it. And this is what you have in the middle term is what you have when you have a universe with an electron and a photon interacting.
Okay, thank you. Thank you.
And we want this Lagrangian to have this property of local gauge invariance, which going back to the previous slide, if I change this psi by some phase, that is not a global phase, but it depends on where you are in space-time. You just plug in that new psi and you apply the Lagrange conditions, and you ask that this Lagrangian is invariant to that transformation. And this term breaks that invariance. So that was the problem that people were trying to work out in the 60s and before that, and how to deal with a gauge interaction where the particle that's mediating the gauge interaction has a mass. Okay, so one way to do that was hit upon was, and the details, of course, are there are a lot of details, but you can think of it as adding a potential energy, of adding a field, but the field should be a scalar field, meaning zero spin, and with a potential that has a particular shape. And it depends on the square of the field and the quartic term of the field with some constants, mu and lambda. And if you plot that out, depending on whether these terms mu squared and lambda are greater or less than zero, you get a quadratic term and a quartic term, which you can make this shape look any way you like. But if you have mu squared less than zero and you have lambda greater than zero, you get an upside down parabola for this term. And then you get a quartic term. So at some point, this quartic term overwhelms the quadratic term. And if lambda is positive, you get this increase in the potential. So we have a potential well in the quantum mechanics sense that doesn't have just one minimum. It has 3 extrema. One is unstable here, and there are 2 stable minima on either side of 0. So phi here is the field value, the field strength, and we're plotting the potential as a function of the field strength. So there, in this model, there are 3 extrema. And yeah, another question? Or is that background noise? Okay, I think it's background. Okay, so we have this potential, and you can think of the curvature here eventually as it's going to be the Higgs boson mass, and you can think of this rise here as the coupling of the Higgs to itself, this lambda term. To skip all the details, if you start with the massless gauge boson and you apply spontaneous symmetry breaking, which means you choose either this minimum or this minimum, actually you choose a circle in that if you rotate this in the 3rd dimension, you choose to be in the well there in the minimum, then what pops out is a massive gauge boson, like the W boson of the weak interaction, and its mass will depend on its coupling, or vice versa. The coupling will depend on its mass, the coupling of this particle to the massive scalar particle, which will be the Higgs boson. So we think about this as a field phi, the scalar field, and the fluctuations of this field, the quantum is the Higgs boson. And for a universe that has a vacuum that's sitting at this minimum, as you have fluctuations, you can go either direction and the energy increases. That the analogy of that is there's disruption of the field by the fact that this quantum, the Higgs boson, is passing through the field and creating ripples in this scalar field. And so the curvature here, the thing to remember for the rest of the talk is the curvature here is related to the Higgs mass, and how strongly the Higgs interacts with itself is how sharp this rise is. Now, there's another point which came later after Higgs. Actually, Weinberg noted that you could also this would give mass to the W and the Z boson, the carriers of the weak interaction. But the fermions are not touched by this. But there is a way to fold them in to the theory and actually to give mass to the fermions by having them also interact with the Higgs boson. So if you combine all of it together, you have a way to describe, starting from a Lagrangian that has massless particles, how you can actually give mass to the particles while still obeying this local gauge invariance, which we want for our quantum field theory. So that was the general idea. 1964 was when it was written down. And it has implications for not just particle physics, but if you think about Big Bang cosmology and how the temperature of the universe has evolved from the beginning. In the beginning, we had a hot universe. And if you think of T as the temperature of the universe, in the beginning is very hot. And there are corrections to this Higgs field based on the temperature. So at very high temperature actually looks like just a single minimum. And so the Higgs field is at 0, so switched off. But as the temperature cooled, as the universe cooled and as it expanded, eventually you get this characteristic shape of the Higgs potential and a very gentle, continuous sort of transformation from a situation where the universe has the Higgs field switched off to where you have spontaneous symmetry breaking and you have to choose, because of quantum fluctuations, fall into one of these minima. And then by now, at temperature roughly 0, we have a universe that has a vacuum expectation value for the Higgs field that's not 0. So 0 would be here. Originally, we start off with no Higgs field, it's turned off. And now we had a Higgs field turned on. So in the evolution of the universe, we start with massless particles that then acquire mass through something called the electroweak phase transition, when we have this transition in temperature from a simple potential to the more complicated Higgs potential. And so that's sort of history of the universe in a cartoon, but explaining sort of how we get from the beginning to where we are now, where the fundamental particles have mass, and also the gauge bosons of the weak interaction have mass. Okay, so once switched on, the Higgs field gives mass to particles while also preserving local gauge invariance. And so that's good. That was the whole idea that we wanted to test at the LHC. And you could ask why we needed an LHC. Why couldn't we do this cheaper, to put it bluntly? And just a brief history, a very brief history of searches before. So this idea it didn't catch on immediately because, okay, we didn't even really have the full quark model confirmed by experiment at that time. But people were thinking about how could you look for a Higgs signature, and the mass scale here is the important part of this plot. We're talking about MeV, from 1 MeV to 100,000, which is 100 GeV, and various neutron nuclear physics processes were checked to see if maybe they were being affected by this Higgs boson, up to a scale, like I said, of 100 GeV. And this was all going on in the 70s and before. This is a summary from 1975. The amusing part is that where this plot ended, just beyond that is where we eventually found the Higgs boson. But I just wanted to flash on a log scale that people were thinking about possibly much lower masses to the Higgs that wouldn't have required a collider. So later in the 70s, people, when they were investigating the consequences of this theory, they noted that if you wanted to have a stable vacuum, that is a minimum that is lower than phi equals 0, then you would want to make sure that any other minima that are around are higher in energy. And so you couldn't just spontaneously tunnel from a minimum here, let's say, a minimum at 0 to something that's lower than that. And you could have a universe, which I'll talk about later, that's actually unstable and would just essentially keep going to negative energy forever. So if you require that the potential energy is always less than it is at 0, that is that you have a stable minimum away from 0, then you can have a minimum mass for the Higgs, and it was roughly 7 GeV. There's another technical aspect of particle scattering, in particular, the weak interaction particle, the charged weak interaction W boson. If you have scattering, then quantum field theory within a model that does not have a Higgs boson would actually give nonsense at high energy. At roughly a TeV, you would have, you'd break unitarity. That is to say, the probability of this interaction would grow larger than 1, which doesn't make any sense. So if you require that that does not happen, that you have a Higgs boson and you have this Higgs mechanism, then it would require that the Higgs has a mass less than a TeV. So by 1980, we had a bound on the Higgs mass, but it was rather large, from 7 GeV to 1,000 GeV or TeV. So there was a broad range to search in, and before the LHC in the tunnel that is at CERN, there was something called the Large Electron Positron Collider, LEP for short, which collided electrons and positrons and searched for the Higgs boson through a process like this, where the electron and positron annihilate into the neutral carrier of the weak force, the so-called Z boson, which would then radiate a Higgs boson. And based on how it decayed, you would search for it this way, which they did very vigorously. And by the time the machine was turned off to make way for the Large Hadron Collider, they had a limit of roughly 115 GeV. So we knew now a tighter limit, not just 7 GeV, but should be greater than roughly 100 GeV. Oops, let me go forward. And then on the other side of the Atlantic, at a place called Fermilab, that had its own Hadron Collider of a lower energy than the LHC, they also searched for the Higgs boson for many, many years. And by 2010, they had, through processes like this, where you have a proton producing gluons that then fuse together into a Higgs particle and then decays in a certain way, they could rule out masses that were in a narrow range. So the final results before the LHC turned on were essentially ruling out a narrow range between around 160 GeV, that it was not that, but it could have been less than 160 or more than 175. So at the start of the LHC, we had a plot like this that as a function of the W boson mass and the top quark mass, the Higgs mass is a diagonal in this plot, and it could have been either in this band, this green band, or in this very large green band up to a TeV. So we had some idea. It was not that we had no idea, but it was a very broad range. And to search it effectively, what we needed was a collider that could probe for a Higgs boson anywhere in this Alad region, anywhere in the green bands. And we needed detectors that could find it at any mass. Importantly, if we did not find it anywhere because of the theory arguments I just made, then we would know it does not exist, at least in the form of the Higgs mechanism that we were searching for. And this was referred to at the time as the no-lose theorem, that either you find it and confirm the Higgs mechanism, or you don't find it, and we know it has that electroweak symmetry breaking has to be driven by another mechanism, not the Higgs mechanism. Okay, so that's the general introduction, and I'm watching the clock, so if I need to, I'll skip over details as we go, but I want to give the general introduction so that you have a context in which to put the sort of where we're going from here. So just a brief image of or a cartoon of the LHC facility, which is near Geneva. This is Lake Geneva and the city of Geneva. So it's just outside, 100 meters underground, a 27-kilometer tube that is evacuated to a very low pressure, in which protons are circulated and collided at various points where you build detectors. So there are various points around the ring that the protons are made to collide at, and then we build detectors around and we try to detect the particles that come out. There are lots of cool facts about the LHC. For me, still one of if you step back from particle physics and think about it, the way the beam is, it's not a continuous beam all the way around the machine. It's actually bunched and into essentially radio frequency buckets. And in each bunch, you have 100 billion protons within a space roughly 5 centimeters long, and the diameter roughly of a couple of human hairs. So it's a very thin beam of particles that are bunched in these little bunches of 5 centimeters, which have 100 billion protons. And then you send them around 27 kilometers at the speed of light and manage somehow to make them collide, which is the wizardry of the accelerator physicists that make that happen at a rate that we can actually do physics. And then there are other cool features of the LHC that I'll let you read offline. So the project has a long history. The goal, of course, was to discover the Higgs boson or rule it out between this range that I just mentioned. But there were other goals to search for new particles, new interactions, signs of anything that was not described by the standard model, supersymmetry, dark matter, black holes even, and so on, or even discover something we didn't expect to discover. That's the most exciting thing to think about. And the first studies were really done in the 80s, and 1984 is when the idea was first started. And from the start of installation, the first collisions, sustained collisions in 2009, it was very short. It was a long lead time, but it was very short, the time between first collisions and the discovery of the Higgs. So how do you produce a Higgs when two protons collide? I briefly showed this in the context of Fermilab, but at the LHC, we collide protons on protons. And this nice picture that I showed previously of a proton being a bound state of 3 quarks is actually much more complicated in quantum chromodynamics. Each of the quarks that we think of as making up the proton can always radiate a gluon. A gluon can always become a quark-antiquark pair, and so on. And so you have inside of the proton, if you get a microscope with sufficient resolution, meaning a particle with sufficient wavelength, that it can see inside the proton, what you would see is a jumble of quarks and gluons. And so what really collides at very high energies, very small wavelengths, is not the proton itself, but what's inside the proton, the so-called partons inside the proton. And this image here gives one example of that, where one proton spits out a gluon, or a gluon inside one of the protons collides with a gluon in the other proton. And in this particular process, they fuse via mostly a top quark loop here into a Higgs boson. So this Higgs boson is a real particle that is emitted in the collision, and its decay products can be detected in the detectors that we build. So this is called gluon fusion, because you take gluons and fuse them together into a Higgs boson. But there are other ways, and I won't go into much detail on this. I just want to show you the pictures. This is what I just explained, the gluon fusion process, but you can have quarks that collide and produce a Higgs boson in various ways. You can have quarks that collide and produce either a WZ boson, which then radiates a Higgs boson, much as it was searched for at the LEP collider. And you could have even more complicated processes where gluons fuse together, but out pops a top quark, an anti-top quark, and a Higgs boson. So these are the four primary ways to produce a Higgs at the LHC. And the cross sections, the rate for each of these processes is as a function of the Higgs mass, is shown on the right. So you can see that it is dominated by this one on the upper left here, but there are other ways to produce it that we have looked at and measured now very precisely, now 10 years on from the discovery. So just to give you an idea of the performance of the LHC at the time in 2012, at the time of the discovery, at the rate that we were taking data, roughly 750 Higgs bosons were produced per hour when we were doing. Of course, we don't detect all of them, but that's how many were being produced if all the theory calculations were correct. So the Higgs boson lives for about 10 to the minus 22 seconds. It has a very short lifetime. And so we don't detect the Higgs directly, we detect what it decays into. And this is a very busy plot, but don't worry about the curves. Eventually, we found it at 125 GeV. So if you focus in on that region, what you see is that, as Kajari mentioned, the favorite daughter, as I like to call it, of the Higgs boson is the B quark. So it preferentially decays to a bottom quark and an anti-quark pair. But then it also can decay to two W bosons of the weak interaction. Gluons actually can decay in the reverse diagram of how it's produced. It can also decay to tau leptons, to two photons down here, and so on. So there are various ways it can decay, and each one has its own rate called the branching fraction. And as nature would have it, as luck would have it, this mass here is the most interesting part of this plot, where it intersects all of these lines for the predicted branching fraction. And so we have many ways for the Higgs to decay, not just one or two as we would have out here. If the Higgs had a mass of 200 GeV, we would be searching for it roughly in these two decay modes. But now at a lower mass, we have access to all of these other channels, and we have many ways. Yeah, sorry, is there a question? No, okay. All right, so the main point, we have many ways to search for it, and so we did. Just to show it in a chart, for the particular mass of 125 GeV, this is the branching fraction, just translating these numbers over here in a plot that's more easily digestible. So again, the bottom quark final state is the most likely, but and the two photon one is very unlikely. However, two photons are very easy to reconstruct, whereas two B quarks are very hard to reconstruct. So we needed to find all of these ways that the Higgs could decay. We need detectors that could efficiently and accurately detect photons, electrons, muons, even tau leptons, the heavier version of the muon, and something we call jets, which is when a quark is produced and hadronizes into a bunch of particles in a highly collimated system that we call a jet. We needed detectors that could do all of that while minimizing the backgrounds.
Can I ask a question here, Jim? So
Sure.
in the previous, so this is the decay pathways, but in the formation pathway, the production of the Higgs, you had four of these diagrams. So the gluon fusion is the primary production pathway. That's what you mentioned. But then are these all sort of theoretical sort of mechanisms? And is there any experimental evidence to measure the fraction from which, which pathway you get how much of Higgs being generated, Higgs bosons being generated?
Yeah, so I showed this plot because it was.
So that's an experimental plot? That's an experimental plot?
This is all theory.
This is all theory. Okay.
Yeah,
okay.
So this is what we expected to see,
right,
if the Higgs boson had whatever mass is down here. So at the mass that we eventually found it at,
right.
If you draw a vertical line, what this is saying is that the theorists, based on the standard model and everything we know about the standard model, predicted the cross section based on this diagram. So if you say that the Higgs is produced this way, there's a way to calculate in quantum field theory what the cross section would be for this process, and so on for the other three processes, and that's what they look like. So it's dominated by this one. That's what we expected. Of course, if there was no Higgs boson, of course we expect nothing.
Right.
But even if there were additions beyond the standard model, that is, other particles that we could stick in this loop, for example, rather than just the top quark or any of the other quarks. If you had a new particle that could couple to gluons and the Higgs, then that would be another diagram
Okay.
Another process to produce a Higgs, which could interfere with the standard model process and produce a cross-section over here that was either higher or lower, depending on whether it was constructive or destructive interference. And so it's a great question that you asked because it highlights the whole point, which is this is what the theorists predicted, and the experiments were measuring the rate for this process directly to find out if it was really this value of roughly 20 picobarns.
Okay.
And if it wasn't, and it could have been bigger or it could have been smaller by some amount. And if it was, and we measured that with precisely enough, we could say to the theorists, the standard model is wrong. And there has to be something else there. Maybe it's a new particle, or maybe there's something else wrong that we don't know about. And that would have been exciting.
Got it. So the prediction was there. What is the rate of production? And that rate commensurated with at least the primary production to be the gluon fusion.
Yes.
Okay.
Roughly.
And if it deviated from that, then you would have said there could be other pathways as well, right? If it was.
Correct. Yeah. Right.
Okay.
So the exciting part of the Higgs search was not just to find it, but to measure it precisely enough that we could state whether it was a standard model Higgs or not. And that's where we're going slowly, but I'll get there.
Sure. And there's
go.
Sorry, there's another question from Sanjay Swain. Sanjay, could you ask your question?
Yeah. So, Jim, I was just curious if you look at this cross-section PP to HX, some of these like PP to TTH and PP to H, somehow they have larger errors, but PP to WH or ZGH, they have very smaller, they're very precisely measured. Is there a reason why there are so much uncertainty in the just H and the TTH?
Yeah, so I mean, generally speaking, the gluons, quantum chromodynamics is harder to calculate than quantum electrodynamics, mainly for the fact that the coupling is stronger. And so the perturbative expansion of the calculation, basically the fine structure constant is a lot smaller than the Higgs, than the gluon coupling. So when you make calculations in quantum chromodynamics, which is the gluons there, and interacting with tops, then there's just inherently more uncertainty in the calculation because you're talking about QCD. Now, there are also quarks here, but they're interacting via the electroweak interaction, which is more easily calculated in terms of a perturbative series when you calculate the cross-section. So that's the main reason why this line and this line are thicker than these lines.
Thank you.
Okay, so we have these targets. So this part I'm really going to skip over because it's too detailed for this discussion, I think. But let me just say we needed large detectors. And the reason we needed, the simplest way to explain why we needed, here's a human down here and other humans down here. So these are very large radius detectors. And the reason is that the particles coming out of these collisions at 14 TeV, 14 trillion electron volts, are very high energy. But we want to measure their momentum. And the easiest way to measure momentum of a charged particle is to make it bend in a magnetic field. From freshman physics, you recall that charged particles bend in magnetic fields. And the radius of curvature of that bend is directly proportional to the momentum of that particle. So if you have a very high momentum particle, you either need a really, really strong magnet or you need a very large moment arm. And in this case, we have both. We have in CMS, we have a 4 Tesla magnet. This silver part here is a solenoid, that superconducting solenoid that produces a magnetic field that's into or out of the page. And as the particles come out, they curve in that magnetic field, and we can measure the trajectory of the particle and determine its momentum from that. That's the main goal of these detectors, is to detect as many particles as possible, measure their energy and their momentum, and thus be able to reconstruct what happened in any particular collision. And because they're large and very complicated, we needed lots of people, roughly 3,000 scientists on each of the experiments, Atlas on the left, CMS on the right, and a very large undertaking to construct them, operate them, and read out the data and analyze the data. Okay, so this is a cross section that I'm going to skip, but just to show you, this is CMS. So the magnetic field is into the page in this picture, 4 Tesla roughly. into the page. And so as the particles come out perpendicular to the beam, the protons collide here, they wiggle in the magnetic field. And we can measure with detectors that detect position of particles. We can map out this wiggle, that's how we detect the particles. And then from the wiggle, we can determine the momentum of the particle, like I previously mentioned. And then there are calorimeters to measure the energy of stopped particles and so on. So it's a very complicated detector onion, a cylindrical onion, as we say, where each piece is designed to make a particular measurement that when taken together, we could reconstruct the particle energy and momentum. I'm going to skip that completely. And but just to note that it's not just signal. When you run the Large Hadron Collider, you have lots of background too. So depending on the final state that all of these different ways the Higgs boson could decay, as I mentioned, depending on the background level and also how well we reconstruct each of the final states, you can get in a plane of how well we reconstruct the decay. That's the detector resolution. So how broad is the Higgs mass reconstructed in a particular final state? If you have a very broad final state, like 2b quarks or 2 tau leptons or 2 w's, you have a very large resolution, and the sensitivity can be worse because you have large background, a very broad signal. It's very hard to see the signal in the background. And so the two modes that we're really targeting for discovery were the 2 photon mode and the 2Z boson mode, which have high sensitivity and very low detector resolution, which means they're very narrow. The Higgs boson constructed from these decay modes is a very narrow resonance on a background, and thus much easier to see from the broad resonances on the top. So the right's just showing that by the time of 2012, we had, with all of these channels put together, high confidence that we could discover the Higgs boson if it existed with something over what's called 5 sigma significance, which means roughly a probability of 1 in a million, or 3 in a million actually, that we were wrong. If we said we'd observed it, but we're actually wrong because it doesn't exist, we would be wrong at the level of 1 in a million. So a very high confidence that if we saw it, it was really there. This is a cartoon that just shows the evolution, and Vivek Sharma gave an excellent talk summarizing the whole history of the discovery, and so I give a link there. You can check it offline. But this is a probability plot. So the deeper this goes, the more probable it is that you found something. So we started off in 2011 with nothing, and then the signal really grew over time, over the course of a year and a half, until we finally had it in the summer of 2012. Not only that, I like to point out at the time, and I still like to point out that in the standard model, there's one Higgs boson. So we found this dip here means it's almost like on a oscilloscope, right? That's why I like this plot. The signal that we saw that was the Higgs boson, we found it at a mass of roughly 125 GeV, but we searched everywhere, as was the original plan, to exclude a Higgs boson up to a TeV. And in fact, we did exclude it everywhere else. So you don't have to know the details of this plot. This black curve is the observed data. And if it had popped up anywhere above 1, we would have found another particle somewhere else that would be a Higgs boson at a different mass. And we did not, all the way up to a TeV. So by 2012 and end of 2012, we had found a Higgs, and we had excluded a Higgs to some level, all the way up to the advertised mass of 1 TeV. So it was quite a tour de force, as they say. And I'm not going to show a lot of plots. In fact, I'm running up on time anyway. But I wanted to show you what it looks like as a function of, in this particular case, the Higgs boson decaying to 2 Z bosons, again, the neutral carrier of the weak interaction, which then decay to 4 charged leptons, either electrons or muons. And so that you gather up all those combinations of the way that decay can go, and you make the mass of the 4 electrons, 4 muons, and so forth. And if you get a peak at a certain mass, then that's something. So over here is, in fact, something vanilla, the Z boson decaying to 4 leptons, a very strong signal there. Above 200 GeV or so, you have continuous production of protons colliding and producing Z bosons, which is a standard model process that's sort of interesting from a standard model perspective, but not what we were looking for. And then right in between, almost Goldilocks mass in between the Z to 4 lepton and this continuum production was a peak that we identified as the Higgs boson. So at least in CMS, it looked like this peak above this background. And so a very convincing visual way to see that we had an excess and in fact consistent with the standard model, Higgs boson. And then, like I said before, we found nothing if you extend this plot out to a TeV. Okay, so now I'm getting to the sort of new part of the topic. And I wanted to talk a little bit about, okay, so there's several ways to measure impact, one of which was that, okay, we made the news. There were more than 1 billion people watching the seminar around the world. And it got a lot of media attention. And I remember at the time, flying on airplanes, people were suddenly interested in what I did, whereas before the Higgs, telling people you're a particle physicist didn't get you very far. But it was very popular at the time and very exciting. It's so exciting that people were actually betting on the Higgs discovery, which this just amused me very much. That as a function of time here, that this was how the volume of trading for whether there's a Higgs boson or not. And this was when the discovery was announced. And so there was a peak before that, which I always thought was insider trading of graduate students on Atlas and CMS, trading on whether the Higgs existed because we knew it did before it was announced. But then it continued after that. It was kind of funny because people were arguing about whether it was a Higgs, the standard model Higgs or not. And so who cares if it is, it's the Higgs. And then people were arguing about whether they should pay or not, if it was the Higgs or something else. And so somebody commented, buyers should have understood from the beginning that science is not very straightforward. So this was happening, in an orthogonal space to science, right? Just people making money, which they eventually did. It was declared discovered. So that's one evidence of the Higgs being discovered. Another measure of the impact, now getting back to science in the field, is that each of these papers from CMS and Atlas have been cited 13,000 times since the discovery. And it was only 2019 when the number of citations per year dipped below 1,000. So we've been having 1,000 citations per year, at least for the last almost decade. And this interest is driven by the fact that within particle physics, the Higgs boson plays a central role, not only in the standard model, but also beyond. And I want to get to that point, that it's not just in particle physics. It touches many different fields of physics and even beyond. Okay, so the first question we had, of course, when you find a new particle, you want to measure its properties with the highest possible precision. And this is what in the abstract I referred to as weighing, photographing, and probing the particle. So we want to know its mass, its quantum numbers, how often it's produced, how it decays, and then what is its full decay width, which means what is its lifetime. And if the particle we found was the Higgs from the standard model, then it should be a zero spin, positive parity, positive charge conjugation, which relates particle and antiparticle, fundamental scalar particle that couples to the gauge bosons, so the force particles and the matter particles, according to their mass, with a single vacuum expectation value, meaning the minimum of the Higgs potential would describe all the masses of the particles we see. And any deviation from this assumption would be a sign of new physics. So I want to show you just briefly the performance of the machine, the Large Hadron Collider, as a function of time. And just to point out that we discovered it with this much data. So the vertical axis is how much data we had. And to put it in context, I give you roughly what this vertical axis corresponds to in terms of number of Higgs bosons that were produced. So in what's called run 1 up to end of 2012, we had roughly 600,000 Higgs bosons produced, and we discovered it halfway through that run. Then there was a long shutdown where we upgraded the machine and the detectors, and then we ran again in the last, between 2016 and 2018, and produced 8 million more Higgs bosons that we used to make measurements with. And so it's a large increase in both luminosity, but also in terms of number of Higgs, almost more than a factor of 10. And so after the discovery, in this run here, which is the most recent run concluded, we had already, with run 1, measured the mass to a precision of 3 per mil, excluded the other spin hypotheses, that it's a pseudoscalar, for example, instead of a scalar, or that it's spin 1 or spin 2 with high confidence. We found 3 of the decay modes, the 2 photon and then the weak decay modes. And we measured the strength, the cross-section times branching fraction, with an overall precision of roughly 15%. So the challenge in this run here with all of this 8 million Higgs bosons was to begin the precision measurement era, where we're really trying to exclude even more, with more confidence than this, the other alternatives that it could be, that it's not the standard model Higgs boson, but something else. We also wanted to discover the other harder decay modes to discover that were harder to reconstruct, but would prove this idea that the Higgs mechanism gives mass to the W and Z bosons, but the Yukawa couplings give mass also to the Higgs gives mass to the fermions through the Yukawa coupling. So we had to detect these decay modes to do that. Just to show you visually what the mass measurements look like, on the left is ATLAS and on the right is CMS. So two different experiments measuring the same thing in different ways. And I won't get into the details, but we measure, the main point is we measure the same mass of this particle, roughly 125 in both experiments. With the precision now, this is not using the full 8 million Higgs bosons of run 2 with a precision of 0.1, so 1 per mil instead of 3. So we improved the precision by a factor of 3 in the last run. Another point to note here is that from the Higgs potential, you recall that the mass, well, it was on the slide, I think I didn't mention it. The Higgs mass is related to the shape of the potential, the shape of the Higgs potential, this quartic term, the Higgs self-energy, and the vacuum expectation value V, which is actually known from muon decay. It's 246 GeV. So if you measure the Higgs boson mass and you know the vacuum expectation value from muon decay, for example, you can actually calculate with basic math what the Higgs self-interaction term should be, and it's roughly 13%. The goal for the future, one of the goals for the future, is to not just believe this calculation because we believe this equation, but to measure this quantity directly and see if it's what we expect within the context of the Higgs mechanism. Okay, so again, skipping the details, but just to show you the kind of signal we have now. When the Higgs decays the 2 photons, this is the size of the signal peak above the background. This is a background subtracted plot. And with this many Higgs bosons fully reconstructed in a very clean final state, you can measure the cross-section as a function of lots of kinematic variables. So it's momentum, how many other particles are produced along with the Higgs boson. So the number of, the topology of the event. And everywhere, the measurements agree with the prediction. Each one of these lines is the standard model prediction. So the message to get from this plot is that any way we slice this signal, so you take all of these Higgs events, Higgs decays, and you slice them in various ways, asking for very high momentum, very low momentum, and more particles or less particles produced. And every time you slice it, you get the same answer, which is the standard model prediction. And now with much higher precision. So as I mentioned, we wanted to see the fermion decay modes of the Higgs to prove this idea that the Higgs gives mass not only to the gauge bosons, but also the fermions. And it's a much more complicated analysis, these 2 decay modes. It's not a very clean peak. This peak here is not the signal. This yellow stuff is standard model vanilla Z boson decays to tau leptons, which has been known for 40 years. The signal is the difference between the red and the yellow. If you zoom in, you might see some white space in between there, the data points and that background. And that difference is the signal, which when you background subtract is a very small signal, which we can see by using the very sophisticated analysis techniques to extract the signal out of this large background. And then similarly for the Higgs boson decaying to quarks that produce these jets that I mentioned before, it's also a very complicated final state and very difficult to see over the background. But this is the level of the signal we have for Higgs decaying to BB bar. So we have found the fermion decay modes. We're further searching then for the second generation particles. So in the lepton sector, that would be the muons. In the quark sector, that's the charm quarks. And there is now initial evidence for Higgs decaying to 2 muons, which you look for, again, in a bump hunt, where you look for the mass of the 2 muons combined. And you don't see it by eye. This is the background. But inside the background, if you subtract that background, then you see a little bump here, which we anticipate with more data will become a very strong signal, just like this one for the 2 photon decay. and it will prove that the Higgs boson does decay to the second generation particles. There are searches going on for Higgs to charm, which is even more difficult than Higgs to bottom quarks, and we're at very early stages in that. Okay, so the summary of the Higgs couplings, that is measurements, going back to the question from before, measurements of how often a Higgs is produced and how often it decays to a particular final state. If you put them all together, if it's really the Higgs mechanism and really the standard model of Higgs, we should be able to explain all of those numbers with a single plot and a single vacuum expectation value, meaning one Higgs boson, one Higgs potential, one value of the Higgs field, this 246 GeV. And if that is all true, if you plot the couplings, so this is just the vertical axis, just the couplings, how strongly they couple to the Higgs, as a function of the mass, you get this on a log plot straight line. And all of the points hit that line. The top quark coupling to the Higgs, the W and Z, the B and the tau and the mu. If there was more than one Higgs or something else going on, these points would not have to lie on a line in this plot. So the visual confirmation of the Higgs discovery is really summarized in a single plot, looking at the couplings and how they relate as a function of the mass and also the different particle types. And there were essentially an endless number of theories beyond the standard model that would have predicted a different relationship between all these numbers. So the fact that they all sit on a line is dramatic confirmation that, in fact, this is the Higgs boson of the standard model with the precision that we have now. Of course, when we get much more data, if deviations appear, it could be that it's mostly the standard model Higgs boson, but maybe a mixture of something else that we could investigate later. So in the final minutes, and please cut me if you really need to cut it off, but I want to answer the question, so what? Did we just get a t-shirt and some cartoons, or was really there something important coming out of this discovery? And one of the main problems coming out of this, questions coming out of the Higgs discovery, is that the idea that there's a maximum mass for a point charge. It's called the Planck mass, and it depends on the gravitational constant. And it's way up there in terms of GeV, 10 to the 19, whereas the Higgs field is down here at 100 GeV. And it didn't have to be this way. A more natural solution would be that the Higgs field was up here at the Planck mass. And so there's a huge question that has been known for a long time. Why is the Planck mass this many times bigger than the Higgs mass, now that we know there's a Higgs and we have measured its mass? This becomes a problem on the real axis. It's not just a theoretical problem anymore, it's a real problem. It's known as the hierarchy problem, and there are various ways to get around it. One way is to just ignore it by saying that we just happen to live in a universe where this happened. And I like to call that the you get what you get and you don't get upset theory. But it's a little unsatisfying. You want to sort of know a reason why this hierarchy exists. And so there are various other ways to solve it. One is to say that, well, the gravitational constant is not really what you think because we have extra dimensions of space. You can't see them, and gravity is actually much stronger when you look at very small scales. That's one way to get around it. One of the more famous ways is supersymmetry, the idea that you have standard model particles and you just make a copy of each one, and then the combination of this additional set of particles cancels corrections to the Higgs mass, which then bring it down to the mass that we actually see, but it's really up there at the Planck scale. But because of this accidental cancellation between particles and SUSY particles, we get this mass that we see. So it's not a problem because the mass is not really what you thought it was. The problem with that, of course, is we haven't seen any evidence of supersymmetric particles at the LHC, which means we've ruled out masses in roughly the TeV range, and that's a problem for that theory in terms of a solution on how we stabilize the Higgs mass. But there are even broader implications for this discovery that go beyond particle physics. And they have to do with the fact that if you believe Big Bang cosmology, the universe has a particular history. And if instead of a very smooth transition from the initial Higgs potential that was very simple, have one minimum, to the one we think we have now, which is this sort of Mexican hat potential, if you had a first order phase transition, much like the bubbling of boiling water, then you could have got this intermediate potential that has 3 minima, but they're separated by a barrier. And so as the temperature cools a little bit and this minimum and that minimum go lower than this minimum, you could have tunneling from a universe that sits at 0 in the Higgs potential, sort of spontaneously tunneling to a universe that has a non-zero Higgs value. And this is sort of visually seen as bubbles, vacuum bubbles in space time. Living in a universe that has no Higgs field, turned off, the original early universe Higgs field, but then having these bubbles where you have a Higgs field and you have particles with mass, and they propagate around and they bang into each other, and they have signatures that you can actually see today in terms of gravity waves. These little bubbles can make gravity waves, but they can also help to explain baryogenesis if you input CP violation, which is in the standard model. This process can lead to baryogenesis, and it would require that there are particles beyond the standard model, not just the ones we know about. And again, like I said, there are detectable consequences for this phase transition in the early universe in the form of gravity waves. So there's a synergy between what we're doing in high energy physics, what people are doing in astronomy and cosmology, looking for dark matter and so on. And this connection is really the Higgs potential. And now that we know that there is a Higgs boson, it makes all of these connections real. Okay, the final point on impact is this idea that we could have a universe whose vacuum is not stable, but in fact unstable. The way this will come about is higher order corrections to the Higgs mass could change the shape of the potential. And instead of having this idea of having a Higgs field that has a minimum that's stable, you could actually have a potential where there's another minimum at a higher energy that's lower. And you could even have a potential that just goes to a negative infinity in this plot. And so you could have tunneling spontaneous from our current universe to one of these other universes, and that would be bad. That would basically destroy, or you would have one of these expanding vacuum bubbles eating the universe. And to avoid that, theorists have sort of mapped out where we need to be in terms of absolute stability, absolute instability, so this curve here, and then some what they call metastability, where you have another minimum, but it's lower than the one we're in now, so we could tunnel there, but it's sufficiently close that it would take essentially so long it wouldn't matter. And it depends on the Higgs mass, and because the Higgs mass depends critically these corrections on the top quark mass, in the plane of the top quark mass and the Higgs mass, you get a bullseye where we are based on measurements, and we seem to be in the metastable region. So in this region where there might be another minimum further away that the universe could spontaneously tunnel to. So, okay, this is not a prediction. This is not like predicting an asteroid will destroy the Earth, but it's just an interesting connection between the Higgs field, the evolution of the universe, cosmology, and the implications for all of that. So I think it's a very exciting time to be an LHC physicist. That's a quote from my colleague at Princeton: "Away from the safety of your home, the universe was not made for your convenience." We sort of want things to be convenient in terms of how we view the universe, that it's natural, for example. And so this discrepancy, the hierarchy problem, having this big difference between the Higgs mass and the Planck mass is unnatural, but you have to deal with that. So just very briefly, the future. So we just ended, well, not just, in 2018, we ended run 2. And the results I showed you were from that run. We're now entering run 3, and we'll run for 4 years at a slightly higher energy, but with twice the rate. So we'll get double the data. And then there's a future that goes out for 20 years, and we'll get 20 times more data. And this is approved. And so this is not a future idea. This is actually going to happen. And so roughly you can think about it, in the next 2 decades, we'll have 20 times more data. And what can we do with it? So in the coming run, with double the data, clearly we're continuing to make more precise measurements. That's the main goal. And I'll have a few examples of the far future where we have 20 times the data. But the idea is to more precisely measure the properties of the Higgs boson, and in particular, the Higgs self-coupling, this lambda parameter, which tells you the shape of the Higgs potential as precisely as possible. And any deviations, again, from the standard model are signs of new physics. Now, I'm going to show you some projections, and they're often pessimistic because data makes us smarter, and data makes theorists a little more creative because the reality of experimental constraints and possibilities motivates deeper thinking. So it's often the case that when you make projections, 10 years before you actually do the measurements are better than what you thought they were going to be because we learned a lot more. So this theory experiment interaction is very important. So briefly, the Higgs couplings, the ultimate precision we expect to get is illustrated in this left plot. For all the various couplings of the Higgs boson to all the particles in the standard model, you can guess based on our current measurements what we expect to get. And the total uncertainty is roughly in the percent range. So we're going from the 15–20% range we have now down to the percent level of precision, which is going to very highly constrain possible physics beyond the standard model that we don't know about. So the idea is to either see some deviation or to say that there is none and thus limit the number of possibilities for what's actually going on. This plot that I showed you before that I said that's the bottom line plot, you can't even see the error bars anymore until you subtract the line. And roughly, again, percent level accuracy on the couplings as a function of which particle you're looking at. There is a way to search for dark matter at the LHC, and not to go into detail, but basically you look for nothing in the detector because the dark matter, if it's weakly interacting, for example, WIMPs, we don't detect it. So it would be missing energy or missing momentum in the detector. And so you can look for something recoiling off nothing. And this something could be a Higgs boson, for example. And compared to dedicated dark matter experiments with some assumptions, so we can put them on the same plot, you see where CMS in particular, also Atlas, can exclude cross sections for dark matter impinging on nuclei, which is how the direct experiments look for dark matter. And for some range of masses, it's actually the LHC provides complementary information. But we don't want to just set limits. We want to observe dark matter. And so we've looked and seen what kind of masses of dark matter, so very heavy dark matter at TeV or more, we could see a signal well in excess of what we would call an observation with the full data that we would expect from the high luminosity LHC era. And then finally, again, this idea of the self-interaction of the Higgs boson, where you have an interaction where a Higgs decays into two Higgses. How often that would happen is called the Higgs self-coupling. It's driven by the Higgs self-coupling. And we measure it, we hope to measure it by observing the production of two Higgs bosons at the same time. And the cross-section, I showed the plot before of the standard model Higgs boson cross-section production. But this is now 1,000 times smaller. So it's much, much more challenging. And where we are now is roughly limits. So in the standard model, you expect a certain value. If you take the ratio of that, then you expect 1 for this parameter. So we're just scaling it by the expectation. So we're expecting to find 1. And the limits we have now are between minus a few and 10 or so. But as we add more data, the idea is to look for this process of two Higgs production and to measure as precisely as we can this shape of the Higgs potential by measuring this parameter to be 1 in the standard model as close as we possibly can. Any deviation from that would again be signs of new physics. So it was a very exciting time 10 years ago. I hope I conveyed some of that excitement to you. The interplay between collider physics and experiments outside of particle physics, cosmology, astronomy, other fields is very real and very vibrant, and it will continue for many decades. I mean, the gravity wave detection program is the same kind of timeline with many improvements to come. So this synergy will continue for this foreseeable future. And in the near future, in the next few years, you should be seeing more exciting results coming from this run 3. And I hope, at least for the young people listening, that I've convinced you that it is an exciting time to be an LHC physicist. So thank you for your time.
Thank you, Jim. That was wonderful colloquium. appealing to many people in the audience and delivered in a very lucid style. So thank you for doing that. And now the talk is open for more questions. So we have already people from the Zoom audience. TP, could you go on, and then I will ask Rajiv Gawai to.
Hi, thanks for a very nice talk. So I have two questions. Firstly, if the claimed W boson mass anomaly is explained by, a Higgs triplet, as has been suggested by some people, the other two in the triplet being electrically charged, what are the prospects for constraining, ruling out, or confirming this at the LHC?
Yeah, so I forget the exact prediction for mass ranges, but the way to do that would be to find, I assume actually also you're talking about charged Higgs in there.
Yes.
So the way to, so just to let everybody know, of course, we've been searching for everything that any idea that a theorist comes up with. Of course, we search for it at the Large Hadron Collider. But the way we would prove or disprove that particular idea, and the idea he's referring to is the latest measurement of the W mass. It appears to be a little higher than what we'd expect from previous measurements. And if that persists, then that has implications, and we need to explain it somehow. So one way to explain it would be to have more Higgs bosons. We have been searching for more Higgs bosons in every possible way that we can. And so the way to do that would be to increase the mass, but also increase the skills, the tools that we have to better look for that. But I don't have off the top of my head the mass range that we would be sensitive to for that particular solution, but it's rather easy to see a charged Higgs, I can say. But do you have enough data to see at a particular mass if you have it? But the signature of a charged Higgs is fairly unique in the standard model, because there's no other charged standard model particle that has a mass above the W mass.
Yeah, thank you.
So it is easy to see. There's a chance to see it, and the particular, like how likely it is to see it, depends on the mass and the theory parameters that you have, and I don't have that number off the top of my head.
My second short question is, suppose it's true that the only supersymmetric particle in nature is the Exino. What is the status of the Exino at the LHC currently? Is it ruled out, or are you still looking for it?
Yeah, we are looking for it. And in fact, we continue to look for supersymmetric particles, even though the sort of low-hanging fruit is not there. And one of the focuses has been over the last run, and will continue to expand in the next run, is to look for electroweak produced SUSY. So the Higgsino is part of that, and it's harder because of the way the production happens and the cross sections that are involved. But we are searching for that, and that is one of the areas where more data actually helps a lot, because we're not at a stage where we're ruling out TeV masses. For electroweak supersymmetric particles, we're at this sort of still 500 GeV range. So there's a long way, there's a lot of potential there of masses to search for that have not been searched for yet, because we didn't have enough data. Whereas for the gluino, as you must know, that it's going to be hard to get a gluino beyond a few TeV because of the energy that we're limited to, which is one of the reasons we would want to go to a higher energy collider in the future.
Thank you. Thank you, TP. Thank you. Professor Rajiv Gawai. Yeah, could you unmute?
Excellent talk, Jim. On your slide 49, you gave a summary of what would be expected after LHC has run its course. Is that right? And if that is the case, LHC would not actually tell us whether the source of the mass around us is really the Higgs.
So this is one of the reasons why people are talking about future colliders beyond the LHC. I wanted to stay on the real axis for this talk, and as you see, I already ran out of time, but of course there are other projects that people are considering to address exactly the point you make, that this is impressive, not what we expected to be able to do, and it's to the, you know, the ability of everyone involved that we could get this far. But you're right, we want to get to the percent level, the 1% level, not the few percent level. And to do that, you would need either a much larger Large Hadron Collider, or a different kind of collider, like an electron-positron collider or even a muon collider, where you could create what we would consider to be a Higgs factory, even though the LHC is also a Higgs factory. And so it's true that at the ultimate precision we'll get, we will get something like this. And like I tried to argue, we could get better than this, but it's hard to say we will get at 1%. And we will have excluded a significant region of phase space, but not all possibilities, of course. So there is a motivation for machines beyond the LHC, and that's one, you highlight one of them, that getting these even smaller.
I actually was referring to the couplings to U and D quarks.
Oh, to U and D quarks. Yeah,
that is what makes up the proton of which I am the rest of the matter.
Oh, I see what you're saying. So that's a different thing. Because actually the proton mass doesn't come from the up and down quark masses.
True, but the U quark mass has to be what it is in order for it to come there.
That's true. Yeah, that's true. So so very briefly, in an electron-positron collider, it's a much cleaner environment. And you can, it's very difficult. It's essentially impossible at the LHC to measure Higgs to up bar or Higgs to down bar. But you can try to get at that with a different kind of collider where you essentially infer it from the measurements that you can make, that you could put a limit on that specifically because of how the Higgs is produced and the environment in which it decays, where you could actually try to separate out the up and down quarks. But yes, you cannot do that at the LHC.
Okay, thank you.
Thank you, Professor Gavai. There's a question here from the auditorium, Professor Gagan Mohanty.
Yeah, thanks, Jim, for a very nice talk. So I had one comment and one question. Comment related to what TP asked. So it would be really, basically one experiment driven this, the WMAS. So it would be nice to see what CMS has to say on that. I mean, it's very difficult, more challenging at LSC than at Tevatron, but clearly we should not, as a poor experimentalist, I would say we should have another experiment getting that result and so that was just a comment. So today we had a talk by this Jan about this Higgs decaying to the fermion just before your colloquium, and he showed a very impressive, like even Higgs to electron, that kind of reaching a sensitivity at the level of muon. So I'm just wondering if you could tell us that when with the full high luminosity LSC data, that what is the expectation for that for the Higgs to electron coupling? Can we get to the standard model level, or what is?
Yeah. I think the answer, first order answer, is yes. Let me go back here. So this is mu. You can, of course, I think CMS was the first to look for Higgs to electron, E plus E minus, and people were laughing because if the Higgs mechanism is correct, then the electron, which weighs a lot less than the other particles, should have a negligible coupling. But we look because why not? We can look, as well as we can look for Higgs to mu, we can look for Higgs to E plus E minus. And so they kind of go together, even though the expectation, because it depends on mass, is a lot smaller for the Higgs to EE. But you can scale this plot, and it must be on the other. So the bottom line is, right now there is evidence, at least in CMS, of at the 3 sigma level. So if you just scale this 20 times more data, you will clearly have enough data to have this bump be significant enough where there's no question that this decay happens, and to have a precision enough to tell whether it is consistent with the standard model at a level that I can't off the top of my head do the math, but you can just scale this plot by up to 3000 from 137. Yeah.
Thank you. Showman had raised his hand. Showman, are you there? Showman, you had a question.
Yeah.
Yeah.
In this slide 28 or something, you had this exclusion plot where you showed up to 1 TeV.
39.
28.
You had this
slide 28.
28
or something where you showed how up to 1 TeV, 200
Yes.
GeV to 1 TeV, everything is excluded. So
This
the
one.
previous one, maybe.
Yes,
Yeah, right,
yes.
right, yeah. So I was just wondering, what exactly are you plotting here? And when you say it's excluded, does it mean that you rule out anything that goes to BB bar, or what exactly is being excluded?
So this was
so first question was, what exactly is being plotted here, and the second question is, what is the decay channel that is being ruled out, basically?
Right. So on the vertical axis is the ratio of cross section times branching fraction of what we observe, and it's combined. So it's all the channels that we look for. We have a cross section times branching fraction that we measure with data, and we compare it to the standard model. And so if the standard model is correct, you get 1, and that's for the line there. And if you see nothing, then you have a limit, meaning you expect to see, based on the theory prediction, a certain number of events. And if you see none, you still have background. And from the background fluctuations, you can calculate a limit on how big could the cross-section possibly be, and we missed it. And that's what's being plotted on this axis. The black points are the data, and they wiggle because you have background fluctuations as a function of mass. But if you don't see a signal anywhere, you can compute how small the cross section would have had to been compared to what you thought it was going to be, and you miss it. So roughly, we would have been sensitive at 200 GeV to a cross section times branching fraction. That's 10% of what we actually expect from the standard model. So highly excluded down here. To see the signal, if I continued this plot to 125 GeV, you would have seen this black line pop up above 1, and that's the signal, that's the discovery that we had. So the fact that this line, the black line, is much lower than the blue line is a very strong suppression or strong limit exclusion of a Higgs boson decaying to what we were looking for as a function of mass. And below 1 everywhere is at least to 95% confidence level is excluded, meant that this plot is telling you that there was no sign of a Higgs boson of a standard model type up to a TeV. Your question about does that exclude BB bar? We don't have the capability at the time. We didn't have the capability to search for BB bar that high mass. We didn't have enough data. So the direct answer to your question about BB bar is no. This is excluding essentially a gamma-gamma, a particle that decays to gamma-gamma like a Higgs would up to a TeV, and also WW and ZZ. The other channels didn't have enough sensitivity to contribute really out here.
Thank you very much.
Thank you. Thank you, Showman. Praveen will have the last question, and then we can conclude this colloquium. Praveen?
Thank you. Thank you, Jim.
Yes.
It's a wonderful talk. Nice seeing you. And my question is, like, towards the end of your talk, in one of the slides, like now, in which you are showing the timeline of the LHC run up until run 6, taking the FCC into consideration, like the run 6, which lies between around 2035 to 2040. Is it like is it established, or it's still at a level of like it's a projection? Yeah, particularly that run 6 and all those things.
I'm sorry, I didn't get the question. So you're asking?
Yeah, because the run 6 extends like beyond 2040, right?
Correct. Yes.
Yeah, taking right now we're considering like with the new European strategy, like they're coming up with the FCC. So is it like run 6 the time frame, and like the run 5, is it established, or it's a projection right now?
So it's planned. I think that's the
It's
correct.
confirmed. That is what I'm asking. Is it confirmed?
Well, I mean, that goes to the question of how does CERN actually do scheduling?
Yeah, I know.
How do they actually do scheduling? But by plan, I mean to say that the project beyond this line, so beyond the end of this decade, the project is called the High Luminosity LHC, and that project is approved. The question you're asking is, will it really run for this many years or not? And
run 5 and run 6.
Okay.
Yeah, and you know the schedule is to confirm how many years will actually run beyond 2029. That's not concrete.
Okay. And I also have one more question. One short.
Praveen, we would actually like to close it because there is another session that is going to follow here within the context of the symposium that TIFR is organizing. Okay. So is it possible you email the question, Praveen, to Jim?
It's a one short question, just one short question. One short question. Yeah, just 1 minute. So Jim is a very high profile person. He's not available so easily. So when that opportunity comes, we have to grab it. So Jim, if in this case, if run 5, let us assume run 5 and run 6 is possible, is it possible to enhance the center of mass energy? I mean, anyway, luminosity enhancement will be there. Is there any plans for enhancement of center of mass energy, or you still continue with the 14 TeV?
14 is the limit.
Oh, good. That's great.
With the current magnets we have, you can't go beyond 14.
Okay. Thank you. Thank you.
Okay. Thank you, Praveen. Thank you, Jim. Actually, this was wonderful. You actually appealed to many people in the audience, even if they are not directly participating in research in this particular field. But thank you for doing that. But I have, and also I would like to compliment your background. It's the NASA hall fully lit up in sun. So we have a special question from one of your, I hope, a person from your grad school.
Hi, Jim. I doubt if you remember me. This is a condensed matter physicist who's been attending your talk. I might just go closer to the camera, I guess. Arnab from the 1992 batch in Wisconsin. I guess you were with Duncan.
I was. Yep.
If you remember me, the only guy from India in your batch.
Yeah. Absolutely.
So it's been a pleasure to listen to you after, I guess, 25 years. And so I'm here at TIFR in condensed matter physics, and recently also moved over to science education. Now that I know you're in Princeton, I have your email. I'll send you a mail. Thanks a lot. It was nice learning about Higgs, for somebody who's completely not in the field. And I mean, I've heard people here give talks over the last 10 years, but it's always good to get the overview. Thanks so much.
Yeah, nice to see you again after 25 years.
Yeah, thank you, Jim. So we will conclude the session. We would have loved to have you here because we have some snacks and tea after this colloquium, which you are going to miss, some Indian fritters, but it's okay. We will have, the next time you come to India, we'll definitely feed you with some. So thank you.
Great. Thank you.
Thank you so much.
Bye-bye.
Thank you. Bye-bye. Thank you all for joining in.